Hello my friends, today we are going to discuss about the new topic, that is the radiographic inspections. So, the term radiology usually implies the radiographic process that produces a permanent image on film or paper. Yes, now you can understand that exactly which I am talking about. So, basically in this particular lecture we are going to discuss about the X-rays and the gamma rays. So, basically we are passing those rays through the samples and then the picture is coming as a film, and then after that just we are recognizing that what kind of problems or maybe the defects are present inside the materials. So, generally the radiographic is a non-destructive testing, because we are not going to harm the element or maybe the substance or maybe the materials, simply we are going to passes those rays through the materials, and then from that we are going to predict the results or maybe get the whole informations. So, it is a one kind of inspection techniques where many types of manufactured components can be examined to verify the internal structure as well as the integrity of the specimen. So, if there is any cracks or pores are present inside the material, so simply we can detect by these techniques. Now, radiography has been expanded usage in industry to inspect it not only the welds and the castings, but to radiographically inspect items such as airbags and the canned food products. Yes, because canned food products it has been already sealed. So, inside what is the conditions or maybe any contaminants are there or maybe some problems. So, we can from outside we can easily get the informations. The objects which can be examined can range in sizes and shapes from micro miniature electronic parts to mammoth missiles or maybe the power plant structures. So, there is no particular size specific testing. So, from a small component to a big large component also we can do this kind of testing. History: radiography started with the discovery of the X-rays as we know by W.C. Roentgen in 1895 and radioactivity by Becquerel in the year of 1896. By using radioactive source such as radium for higher photon energy could be obtained than those from normal X-ray generators. Soon X-rays and gamma rays found various applications. Nowadays we are extensively used these X-rays or maybe the gamma rays. These rays were put to use very early before the dangers of ionization radiation were discovered. After World War II, new isotopes such as cesium 137, iridium 192 and cobalt 60 became available for industrial radiography, and the use of radium and the radon has been decreased. Now, what are the basic principles, how it works? So, the part first, whatever the part we are going to check, that is placed between the radiation source and a piece of film. So, it is simple like a camera. So, the part will stop some of the radiations, thicker and more dense area will stop more of the radiations. The unabsorbed radiation exposes the film emulsion similarly to the way light exposes the film in the photography, as I told already. Now, development of the film produces an image that is two dimensional shadow picture of the object. So, from this particular case you can see that we are having that test piece over here. Now, the radiation source is coming, then after that we are having the film, and if we see the film, so simple we can get the image of our defects onto the film itself. But sometimes it may difficult to get its actual area or maybe the actual locations, but if we take that image from the different sides, so simple we can get the whole informations about the location of that particular defects. Variations in the density, thickness or compositions of the object being inspected causes variations in the development of the film. Evaluation of the radiograph is based on a comparison of the differences in the photographic density with known characteristics of the object itself or defects present in the test object. So, sometime to see certain kinds of crystal structure or maybe the morphology also we are doing this kind of testing. Now, what are the essential elements for the radiography testing? So, first is that a source of penetrating radiation such as an X-ray machine, or maybe sometimes we are calling it as a X-ray gun. The object to be radiographed such as the weldment or maybe the casting or maybe any kind of products, as I told already. Third is the recording or maybe the viewing device, usually photographic film enclosed in a light tight holder. Number 4, a qualified radiographer trained to produce a satisfactory exposure, because sometimes we need to do the proper X-ray testing, so that we can get the actual informations of that particular defects itself. And the last one is that a skilled person, that is a very important thing, because after getting the film then only you can recognize that whether this is the image of some elements or maybe some cracks or maybe the some voids or maybe the some pores. So, that interpretations, so that is why a highly skilled labor or maybe the operator is required. Now, first one is called the penetrating radiations. What is that? The radiation used in radiography testings are X-rays and the gamma rays, as I already told you. They are a form of electromagnetic radiation similar to the visible light. Unlike light, however, they have higher energy, shorter wavelength and the ability to penetrate, means it is having very higher energy, so that it can go inside the material itself, travel through and exit various materials such as carbon, steel and other metals. When the components are subjected to radiography, these radiations travel and are transmitted through them in different amounts by different materials depending upon their radiological densities. Say suppose different materials is having different densities. So, after that when we will get the image in the film itself, so there should be some different types of colors we can observe, that will be depending upon the densities of different materials. Radiological density is determined by both the density and the atomic number, the number of protons in an atom's nucleus of the material being imaged. So, now you can see this is the whole spectrum. We are having electromagnetic spectrum starting from radio waves to gamma rays. So, this is the visible light spectrum. So, this one we can see by our normal eyes, and then after that when we are talking about the short wavelength, so that time we can find that X-rays and the gamma rays, which is having a very high frequency and short wavelength. Now, if we talk about the spectrum table, so you can see that in X-rays the wavelength is generally 0.01 to 10 nanometers, frequency is 3 into 10 to the power 16 hertz to 3 into 10 to the power 19 hertz, and the photon energy is 120 electron volt to 120 kilo electron volt. And if we talk about the gamma rays, then it is less than 0.01 nanometer, more than 10 to the power 19 hertz. So, you can see that the power of gamma rays are better than the X-rays, and here the photon energy for the gamma rays is more than 100 kilo electron volt. Now, come to the X-rays. So, they are form of electromagnetic radiations having wavelength ranging from 0.01 to 10 nanometer, that we have already discussed in our last slide. Now, how we are generating the X-ray, that means production of the X-rays. So, generally X-rays are produced when fast moving electrons emitting from heated filament by thermoionic emission are suddenly brought to rest by colliding with the matter. So, you are generating a thermionic emissions, so that the electron will move from one place to the another, that means from hotter to the colder one. Electrons are accelerated through a potential difference and directed towards a target material. When these electrons strike on target with very high velocity, X-rays are produced at the point of impact and radiated in the all directions. So, if we see this kind of image or maybe the pictorial view, so here we can see that we are having that anode. Now, anode is our target or maybe that our materials, and then we are having the cathode is nothing but the filament. So, now we are generating a thermionic emission over there, and there is a huge potential difference in between the cathode and the anode. So, that here the electron density in the cathode side is more. So, automatically the electron will move from the cathode to the anode side and it will hit the specimen. Now, when it will hit the specimen, it will generate the X-ray, and that X-ray will penetrate into the substance, and after transmitting it will fall upon your film and it will generate the image itself after developing the film. So, the kinetic energy of the accelerated electrons can be converted in 3 different ways. First, a very small fraction, that is less than 1%, is converted into X radiation. Approximately 99% of energy of electrons is converted into heat by increasing the thermal vibrations of the atoms of the target itself. Some of the electrons have sufficient energy to eject orbital electrons from the atoms of the target materials which are ionized. Now, what are the mechanisms? So, there are two different atom processes that can produce the X-ray photons. So, first one is called the Bremsstrahlung. So, it is a German word, and second one is called the K-shell emission. So, when you are talking about the Bremsstrahlung, Bremsstrahlung is a German term meaning the braking radiation. In this process, a high speed electron travelling in a material is showed or completely stopped by the force of any atom it encounters. So, this is the pictorial image over there. So, now we are having the k orbital, l orbital, m orbital. So, now you can see that we are having that electrons. So, now the electron will directly hit the target itself. When we are talking about the K-shell radiations, so in this particular case, when the incoming electron give enough energy to knock K-shell electron out of its energy state, then electron of higher energy can fall into the K-shell. The energy lost by the falling electrons shows up in an emitted X-ray photon. So, now simple the thing is that here the electron will change its position. So, it will come to the K-shell, means the outermost shell. Meanwhile, higher energy electrons fall into the vacated energy state in the outer shell and so on. So, that is a continuous process. So, first the electron is inside, it will come to the K shell, and then after that it will be radiated, and so inside electron again it will come to the K shell and it will be radiated. So, it is an continuous process. Now, K shell emission produces higher intensity X-rays than the Bremsstrahlung, and the X-ray photon comes out at a single wavelength. Both atomic processes can occur in the heavy atoms of tungsten, which is often the material chosen for the target or anode of the X-ray tube. High energy X radiation. Examination of thicker sections is carried out using high energy X-rays whose energy value is 1 mega electron volt or more. Using high energy X-rays, possibility of large distance to thickness ratios with correspondingly low geometrically distortion, short exposure times and high production rate can be achieved. Also, small focal spot size means how much area you are going to cover onto your surface itself, and reduce amount of high angle scattered X-ray reaching the film result in radiographs with good contrast, excellent penetrometer sensitivity and good resolution. Example, high energy X-ray radiography is currently used to scan intermodal freight cargo containers in the many countries. So, when the truck from one country to another country, it is traveling with some product. So, it is a big size. So, simple, we are passing that truck container through the X-rays and we are getting the image. Not only that, best example is that we are using these techniques in the airport itself for scanning our luggages. So, now we are coming to the gamma rays. They are the electromagnetic radiations of the shortest wavelength and the highest energy. They are identical to X-rays, except that X-rays are artificially produced and gamma rays are naturally occurring. Gamma rays are emitted from an unstable nucleus. Each isotope with unstable nucleus will have characteristic nuclear energy levels and intensities for the emitted radiation. In contradistinction to X-ray machines which emit a broad band of wavelengths, gamma ray source emit one or few discrete wavelengths. The gamma ray energy level remain constant for a particular isotope, but the intensity decays with time as indicated by the half time, because its life is going to be reduced. So, now in this particular case you can see that we are having that heavy unstable nucleus, and then after that the spontaneous decay means its life is decreasing, and then it is forming dividing into three parts. One is called the alpha particle, that is the helium nuclei, then it is generating the gamma rays over there, and the rest is that composed by neutron, proton and the beta particle. So, this way we are generating the gamma rays. Now, gamma ray source, Most of the radioactive material used in industrial radiography are artificially produced by subjecting stable material to a source of neutrons in a special nuclear reactor. In this activation process, an extra neutron is introduced to the atoms of the source material. As the material rids itself of the neutron, energy is released in the form of gamma rays. So, knowingly we are introducing one extra neutron like a doping inside the material to make it unstable. Selection of radioisotopes for the purpose of radiography is usually done on the basis of half life, intensity of gamma rays produced and the cost of the production itself. The four most popular radiographic sources are cobalt 60, or generally we are calling it as a CO 60, thulium 170, cesium 137 and the iridium 192. Now, production of the gamma ray isotope. So, generally cobalt 60, iridium 192 or maybe the thulium 170 are produced by N and the gamma reactions, example for CO 60. So, generally N plus cobalt is equal to cobalt 60 is equal to gamma plus gamma, that means it is generating the gamma rays over there. Cesium 137 is separated out from the fission products of the irradiated reactor fuel. Now, some important characteristics of most popular radiographic sources like half life of the cobalt 60, you can see it is 5.27 years, but if we are talking about the iridium 192 it is 74.3 days. If we talk about the cesium 137 it is 30.1 years, and if we are talking about the thulium 170 it is nothing but the 129 days. So, now if you see the energy, so in this case cobalt 60 it is 1.33 to 1.17 mega electron volt, and that is the highest one compared to others. If we talk about the radiation output, then it is cobalt 60 is giving the 1.35, that is also the highest one. If we talk about the size for cesium 137 is the higher side, that is 10 millimeter. Steel thickness which can be radiographed, it is generally 200 millimeter, 75 millimeter, 40 to 100 millimeter and the 10 millimeter. So, from this particular case you can get the cobalt 60 is the best one among these four. Now, common properties of X-rays and the gamma rays, they are not detected by the human senses, as I told already we can not see it by our normal eye or maybe the naked eye, we cannot feel it, we cannot hear it. So, we cannot recognize it by our organs. They travel in straight lines at the speed of light, their paths cannot be changed by electrical or maybe the magnetic field, they can be diffracted to a small degree at interfaces between two different materials, they pass through the matter until they have a chance encounter with an atomic particle. Their degree of penetrations, as I told already, it depends upon the thickness of that particular materials, its activation energy and the matter they are travelling and what is the density of that particular material. They have enough energy to ionize matter and can damage or destroy the living cells. Now, come to the imaging. Now, we have already gone through the sources. Now, how to take the image? First, it is divided into two parts depending upon the important factors. One is called the energy of the penetrating radiations, another one is called the geometric factors of the inspection systems. So, when we are talking about the energy of the radiation affects its penetrating power. Yes, of course, if its own power is very high, so that means automatically it will go inside the material itself more. Higher energy radiation can penetrate thicker and more dense materials. Radiation energy or maybe the exposure time must be controlled to properly image the region of interest. So, in this particular case, if we are getting the low energy radiations, so we can get some kind of blurred image over there. When we are talking about the high energy radiations, so in that particular case we are getting a clear image. Now, come to the geometric factors. So, generally the following are the geometric conditions must fulfill for surface true shadow of the object itself. So, we can get the real image. So, first one is that source size should be as small as possible. source should be as far as possible from the object itself. The film should be closest to the object. X-rays should be directed perpendicular to the recording surface itself. So, it is like this, plane of the object and film should be parallel. The volumetric extension of the defect or flaw orientation should be parallel to the direction of projections, okay, which we are going to discuss shortly. Now, what is the flaw orientations? So, thing is that how you are going to put your gun so that you can get the best image. Radiography has sensitivity limitations when detecting the cracks itself, because from the outside we do not know that how the cracks are present inside the materials, whether it is into the horizontal positions or maybe the longitudinal positions, or maybe it is creating some kind of angles over there. So, what kind of cracks we do not know from the outside. So, now penetrating radiations see a crack as a thickness variations, and the larger the variation the easier the crack is to detect. If it is very hairline, so automatically either we can get a very fine line over there, or maybe sometimes we cannot detect it. When the path of the rays is not parallel to a crack, the thickness variation is less and the crack may not be visible. Yes, of course. Say suppose the we are having that samples and the cracks are present inside the material like this, and we are passing the X-rays from the top itself, as I told already it should be the perpendicular one. So, automatically we cannot get the width and thickness properly over there, or maybe it is having some kind of inclinations. If it is something like that, then from the top you can get a clear image over there. Same thing we are talking in this particular case. So, in this particular case if you see that this is not easy to detect, but when the radiation is coming in this, so automatically you can detect this all the dimensions. Now, imaging modalities. Several different imaging methods are available to display the final image in industrial radiography. First one is called the film radiography, and second one is called the digital radiography. It includes the computed radiography, real time radiography, direct radiographic imaging, and the computed tomography. So, in this particular case you see that nowadays when you are talking about the X-rays normal for the medical purpose, now they are calling it as a digital X-ray. So, earlier we are not getting the very sharp or maybe the proper image, but nowadays we are getting a very sharp and proper image. So, you can see that for MRI or maybe something like that, it has been written some kind of CT scan. So, that means computed tomography scan generally we are talking about. So, we are getting a very clear image of our body parts. Now, let us talk about the film radiography. It is most widely used and oldest imaging mediums in industrial radiography is radiographic film. In this method, a two-dimensional latent image from the projected radiation is produced on a sheet of film that has been exposed to the unabsorbed radiation passing through the test piece. Film must be protected from visible light. Light, just like X-rays and gamma rays, can expose films, hence it is loaded in a light proof cassette in a dark room. So, if the normal light will fall onto this film prior to the testing, so this film will be damaged. So, that is why generally we are using a very dark room over there. This cassette is then placed on the specimen opposite the source of the radiations. In order for the image to be viewed, the film must be developed in a dark room. The process is very similar to photographic film development. Earlier also when we are using that film roll into our camera, also after taking the picture also we are using this kind of techniques to develop the image or maybe the photograph. Film processing can either be performed manually in open tanks or in an automatic processor. Once developed, the film is typically referred to as a radiograph. So, now you can see radiographic generator we are having that specimen, and then here you can see the image into the film itself. So, you can see the crack, you can see the pore, you can see the channel, you can see the hole. So, all kind of images will come onto the film itself. Now, what is the structure of the radiographic film? Composition of radiographic film is similar to that of a photographic film and contains several layers. First one is called the top coat layer. to prevent emulsion from scratches, pressure or contaminations during use, because after taking the image we are putting it into in front of some visible lights, and then we are seeing that how the image has been come, or maybe we are putting it into some envelope so that it may be it should be scratch proof, or maybe it should be some kind of contamination free. Next one is called the emulsion layer. Radiation sensitive emulsion layer is coated on transparent film base. The emulsion consists of the gelatin containing light sensitive silver halide crystals such as AgBr and the AgCl. The light sensitive crystals change shape when exposed to light, which are then converted to a dark metallic silver, giving us the image generally that we see. So, at the time of developing, some kind of chemical reaction is going on. So, the material is changing, and after that we are getting the exact image over there. Next one is called the adhesive layer to achieve firm attachment of the emulsion and backing layer with film base. Next one is called the film base to provide support for emulsion layer and to transmit light to view the image itself. Then backing layer to prevent film curling due to swelling of emulsion during processing, to prevent reflection of stray light from the film support materials back into the light sensitive area. So, you can see if we do the cross sectional of that particular film, we can see the top coat, then emulsion, then adhesive, then film based support materials or maybe the plastic, then both side we are giving the adhesives and another one we are giving the backing. So, when we are holding that film, it should not be bent. So, best example is that normally any kind of X-ray film is available in our home. So, if we hold it or maybe the touch it, then we can see these all are the different layers has been put onto that particular film. Now, come to the digital radiography. So, it is the one of the newest form, as I told already, of radiographing imaging is digital radiography. Requiring no films, digital radiographic images are captured using their special phosphor skins or flat panels containing microelectronic sensors. No darkrooms are needed to process films, and captured image can be digitally enhanced for increase the detailing. Images are also easily stored when in digital form. There are a number of forms of digital radiographic imaging includes real time radiography or maybe the RTR, computed radiography or maybe the CR, direct radiography or maybe the DR, and the last one is called the computed tomography, that is the CT. Now, first come to the real time radiography. So, RTR or maybe the real time radioscopy is a non destructive test method whereby an image is produced electronically rather than on film, so that very little lag time occurs between the item being exposed to radiations and the resulting image, because after material then it is coming onto the film itself. So, there is some little bit lag time. So, when the electrons is hitting your materials and when the electron after passing it is hitting your film. So, there is a time gap in between these two occurrence. Because image acquisition is almost instantaneous, radiographic image can be viewed as the part is moved and rotated. What are the advantages? Manipulating the part can be advantageous for several reasons. First is that it may be possible to image the entire component with one exposure. Second, viewing the internal structure of the part from different angular perspective can provide additional data for analysis, and the last one is that time of inspection can often be reduced. So, very quickly we are getting the image of our materials. Working procedure of the real time radiography. So, generally the fluorescent screen uses materials that fluorescence when struck by radiation and produces luminescence during the period of irradiation coming from the test object itself. Image intensifier converts X-rays and gamma rays coming from fluorescent screen into visible light at higher intensity. A special camera which is very sensitive to a variety of different light intensities captures the light output of the image intensifying screen. The captured image is then processed and viewed on the display device or maybe the monitor. So, here we are having that radiographic source, now we are having that samples, now we are having that fluorescent screen over there, now we are having that image intensifier, camera, image processor and the monitor. So, that means a very small image is coming over there, and now just we are enhancing its size, so that we can clearly see the image of that particular cracks or pores or maybe the defects. Next one is called the computed radiography or maybe the CR. It uses a phosphor imaging plate that replaces film in conventional radiography techniques. CR requires several extra steps compared to the direct radiography. First, it indirectly captures the image of a component on a phosphor plate, and the second then converts the image into a digital signal that can be visualized on a computer monitor. Image quality is fair, but can be enhanced using appropriate tools and the techniques, that is the adjusting the contrast, brightness without compromising the integrity or maybe without compromising the image quality. It is important to know how tools such as adjusting contrast affect the image. Care should be also be taken to make sure minor defects are not hidden after enhancements are made. Sometimes it may happen that we are increasing the contrast or maybe the brightness. So, what will happen, maybe a very hairline cracks we cannot see by just giving the extra contrast or maybe the brightness. So, that we have to adjust, so that we can get the whole image very clearly and sharply. What is the working procedure? As a laser scans the imaging plate, light is emitted where X-rays or gamma rays stimulated the phosphor during exposure. The emitted light is then converted to a digital value using analog to digital converter. So, in this particular case you can see that here we are having that laser beam. So, we are having that optical scanner over there. So, it is hitting, and then we are having that imaging plate over there. So, on top of that it is creating the image, and then we are having that photomultiplier tube, and through AD analog to digital converter, and then directly it is coming as some digit or maybe directly. That means what? Computer only understands 0 and 1 value. So, when there is some signal, some sorts of signals are coming, then the computer is converting that signals into some images and we are getting the information. Next is called the direct radiography. So, generally the direct radiography is a form of real time radiography that uses a special flat panel detector. The panel works by converting penetrating radiations passing through the test specimens into minute electrical charges. The panel contains many microelectronic capacitors. The capacitors form an electrical charge pattern image of the specimen itself. Each capacitor's charge is converted into a pixel which form the digital image over there. So, now here the simple is that electronically we are capturing the image of our defects or maybe the of our samples. Next, come to the computed tomography. So, classical digital radiography techniques cannot deliver any depth information of defects in their radiographic images, as they are purely 2 dimensional. As I told already, it will give you the 2 dimensional image, but when you are talking about the 3 dimensional image, we are coming to the computed tomography. That is why if you see the CT scan, it is giving you the 3D view of our skeletons or maybe of our body parts. So, computed tomography is a powerful technique for producing the 2D and 3D cross sectional images of an object itself. It uses a real time inspection system employing a sample positioning system and the spatial software. So, in this particular case you can see that we are having that radiographic source. So, either gamma or maybe the X-ray beam are generating, then we are having that test component over there, and we are having that image intensifier. So, now analog and video signals is coming directly to the computer, and here we are having one turntable interface unit also. So, in that particular case the sample is rotating into the different angle or maybe the directions, and through that we are getting a real time inspections or 2D or maybe the 3D image directly into the computer itself. Now, what is the working principle? Generally, tomography means imaging an object by taking measurements from slices of its cross section. Example, radiographic inspection of tensile specimen. Step 1, CT slices through several locations of a tensile specimens are captured using the CT inspection tables. So, in this case you can see CT slices at different cross sections. Now, come to the step 2, a number of slices through the object can be reconstructed to provide a 3D view of internal and external structural details. So, compiled or maybe the reconstructed radiographic images, and the step 3, the resultant 3D image can then be manipulated and sliced in various ways to provide through understanding of the structures itself. So, this is the slide 3D image for inspections. So, first it is taking, suppose you are having one object, now it is dividing your object slice by slice, and then each slice it is taking the image, then automatically after adding all the slice it is creating a 3D image, and then after that it is giving a clear inspections or maybe the clear results of our test specimen. Now, how to interpret the radiographs? To identify the discontinuity on the radiograph and correlate them with their appearance and locations in the actual object, the essential steps in interpretations are as follows. Sometimes it may happen that maybe pores or cracks are almost looking like same, or maybe some holes or maybe the pores are looking like same. Now, you need a trained operator or maybe trained person who can judge properly that whether this image is exactly for the cracks or maybe the pores or maybe the holes or maybe some other else. Now, to determine the accuracy of the identifications of the radiograph, determine the workpiece material and the manufacturing processing setup, verify the radiographic setup and procedure, review the film under good viewing conditions, determine if any false or irregular indications are present on the film, identify any surface irregularities and verify their type, evaluate relevance of discontinuities with code or specification requirement, and prepare the radiographic report. So, generally the interpretation of radiographs in the weldments. So, I am giving an example. So, for defects like porosity, round or elongated smooth dark spots will come onto the film itself or maybe into the image. If it is slag inclusion, dark irregular shapes. Incomplete penetration, continuous or intermediate dark lines in the middle of the weld. If it is tungsten inclusions, white areas of round or irregular shapes. If it is lack of fusions, thick dark line. Now, the thing is that at a first instance we cannot predict the exact thing what is going on inside or maybe what is present inside the materials. A really highly trained operator or maybe that scientist can say that what is the cracks are present inside the material from their experience. Now, what are the advantages and limitations of the radiography testing? If we talk about the advantages, first one is that information is presented pictorially, permanent record is provided which may be viewed at a time and place distant from the test, useful for thin sections, access into small cavities, technique is not limited by material type or density, can inspect assembled components, minimum surface preparations required, sensitive to change in thickness, corrosion, voids, cracks and the material density changes, and detects both surface and the subsurface defects. Of course, there is certain limitations. What are those? Possible health hazard, need to direct the beam accurately for 2-dimensional defects, film processing and viewing facilities are necessary, not suitable for automation, high initial cost, many hours of technician training prior to use, access to both sides of samples required for getting the exact information, orientation of equipment and flaw can be critical. Now, if we just make a comparison in between the X-rays and gamma rays radiography. So, what are the advantages of the gamma ray radiography over X-ray radiography? First is that no electrical or water supplies needed, equipment smaller and lighter, more portable, equipment simple and more robust, more easily accessed, less scatter and greater penetrating power, equipment initially less costly. But when you are talking about the disadvantages of the gamma ray over X-ray, so it is poorer quality radiographs, exposure times can be longer, sources need replacing, radiation cannot be switched off, poorer geometric unsharpness, remote handling necessary. So, these all are the drawbacks of gamma rays over X-rays. And last is called the radiation safety. So, now ionization radiations whatever may be, whether it may be the X-rays or maybe the gamma rays, is an extremely important non-destructive testing tool, but it can pose a hazard to human health. For this reason, special precautions must be observed when using and working around ionizing radiation. Complicating matters further is the fact that gamma and X-ray radiations are not detectable by the human body. However, the risk can be minimized when the radiation is handled and managed properly. There are three basic methods of providing the protections. First one is that introducing the absorbing materials around the source, maybe some electrons which will not pass through the materials, it will scatter or maybe it will be reflected from the material itself. So, we have to take some kind of protection, so that reflected electrons can be absorbed by some other material. Second, increasing the distance between the source and the personnel, the radiation dose rate at any point depends inversely on the square of the distance from the source itself. So, we have to maintain the keep safe distance. Third, reducing the time that is necessary for personnel to be near the source itself. So, reducing the time. Now, radioactive source handling equipment. Pallet of radioactive material cannot be safely handled except by the special methods. Apart from hazards of radiation from source, there would be contamination hazards from particles of radioactive matter wiped off by anything touching the pallet. Artificial radioactive source for gamma radiography are always supplied as sealed sources in a capsule by the Atomic Energy Authority of the supplying country, because these all are the some kind of health hazards materials and environmental hazard materials. So, we are going to keep that materials or maybe transferring that materials with a very high security and safety. There should be no need for the industrial radiographer ever to encounter the problems of handling unsealed sources. For transportation and handling, the radioactive capsules must either be supported by a mass of material which absorbs sufficient radiations for the dose rate on the outside of the container to be reduced to a safe level, using long tongs, a long rod, or by other remote control handling equipment, so that the distance between the source and handler reduces the dose rate to a safe value. Now, we have come to the last part or maybe the last slide of this particular lecture. So, now if we summarize the whole lecture. So, in this particular lecture we have talked about the radiographic inspections, which is nothing but the taking the image of that particular materials. So, either we can do it by two methods, one is called the X-rays, another one is called the gamma rays. An X-ray generator or radioactive isotope is used as the source of radiations, and radiation is directed through a part onto a film or maybe some other detector. Material thickness and density changes are indicated as lighter or darker areas on the film or maybe the detector. Radiographic examination finds many applications like casting, welding, structures, for internal soundness. So, there are n number of applications nowadays we are using this kind of rays over there, even if for the biomedical applications too. Thank you.